Okay, so today I'm going to be talking about the state of physics uh, roughly prior to the um, development of quantum mechanics. So I'm talking about sort of the state of physics, what physicists and scientists knew prior to about 1905 to sort of 1915, kind of when the quantum got started. In particular, I'll be talking mostly today about classical mechanics because there are some aspects of classical mechanics that we will um, be using some concepts that, of course, that will also be useful for uh, quantum mechanics. And so the state of the of physics, mostly includes classical mechanics, thermodynamics, and electromagnetic theory. So up until this point, up until the sort of dawn of the quantum theory, physics seemed fairly complete. There was sort of classical mechanics, Newton's equations, Laplace, Lagrange, and so on. They could accurately predict the trajectories of projectiles. Uh, they could predict planetary orbits and so on. So very successful, starting with Galileo and up through the 1800s, very well developed. And it seemed like a solid, self-contained theory. Another area where it seemed like physics was almost complete was in thermodynamics and chemical thermodynamics. So this understanding of heat and work that sort of started with things like steam engines and progressed through a series of scientists who contributed a lot, kind of culminating in the work of J. Willard Gibbs and James Clerk Maxwell, who really tied it all up together into a neat set of laws and really developed all of the math very similar and exposition of the theory in a way that's very similar to what is taught and used today. Similarly, electromagnetic theory appeared to be a fairly complete theory, starting with various scientists, including Faraday, and kind of culminating in Maxwell's equations, which really sort of tied electricity and magnetism together in a unified theory and governed by a nice set of equations using the using the vector calculus that was developed by Gibbs uh, in in explaining his thermodynamics, and that was also sort of simultaneously developed by Heaviside, a British mathematician. However, we use Gibbs' uh, formalism for vector calculus. So the next thing I'd like to work on is I'd like us to start talking a little bit about classical mechanics. So classical mechanics, we have uh, concepts like work. Work is minus the integral of force dot dx. Very useful concept, and of course is kind of the foundation of also thermodynamics, but it also shows up and it ties thermodynamics to classical mechanics as well. And it brings up the concept of force. And force, of course, is important in understanding Newton's equations. So we know that Newton's laws say that force is equal to mass times acceleration. in typical SI units, that would be force would be given in newtons, which is kilogram meters per second squared. And yeah, kilogram meters per second squared is newtons. And then defining a few additional things, that leads us to acceleration. What's acceleration? We can think of acceleration as being the first derivative of velocity with respect to time. And velocity is the first derivative of position with respect to time. So dx dt. So a is dv dt, v is dx dt. And therefore, if you know force, position, and velocity at some given time, say t0, then you can just integrate Newton's equations and extrapolate to any point in time. So if we know exactly the position, velocity, and time, and at a given precise time, then in principle we can extrapolate to any point in the future or in the past and predict exactly how the system is going to behave. And this is, of course, seen in being able to predict planetary orbits and lunar orbits for centuries or millennia at a time. And so this regular motion is often referred to as a clockwork universe. And is kind of a hallmark of the physics at the time prior to quantum mechanics. So let's introduce some additional concepts from classical mechanics that we'll also use. One is the concept of momentum. We'll use typically the symbol P. Momentum is mass times velocity. Also, momentum is another one of these things that's conserved. There's a conservation law associated with momentum, and so that ends up being important and useful in some cases. In addition to work, something kind of similar to that is kinetic energy, in that a particle with kinetic energy can, say, do work on some other object, such as if you have a projectile, a rock thrown at a piece of clay. The rock is initially going to have some kinetic energy associated with it, and then that kinetic energy does work on the clay to deform the clay. So that's one example of conservation of energy. Energy is also conserved. So, kinetic energy is given by 1/2 mv squared. That's the energy of a particle moving. If you have a collection of particles, of course, you just sum up the various kinetic energies of the various particles. You can also refer to kinetic energy in terms of momentum, right? Since momentum is mass times velocity, then we can rewrite kinetic energy as p squared over 2m. And conservation of energy, we talked about the kinetic energy being able to do work. Also, kinetic energy and potential energy can be related. And the conservation of mechanical energy is often written E equals K plus V, where V is potential energy. And potential energy, you can think of, say, the potential energy is the energy that a system has that's not associated with motion, but it's associated with an energy that has the potential to cause either work to be performed or the ability to impart kinetic energy to some object. So here's a quick example, and hopefully I will assign a homework that will go into this in a little bit more detail. But let's look at a pendulum. If we take a pendulum has some sort of arm and has a mass or a weight, and we can imagine pulling the weight, to the left here, and then letting the system go, and then the weight is going to sort of fall, but in a orderly way, in a sort of swinging motion down to some point B, where the swing arm is vertical, and at that position, the kinetic energy is at a maximum, and the potential energy would be at a minimum. We could set that minimum to 0. We're sort of free to set where our potential energy scale is. There's really no rule that says we have to set it to 0 there, but it's convenient to set it to 0. And then that kinetic energy, of course, is going to end up, the weight will continue to move up until it reaches some point where it slows down and stops, and all of that kinetic energy has been converted back into the potential energy associated with raising the mass by some amount, by some height. The height, of course, we can determine from the sort of angle and the length of the leather, the length of the swing arm. And that's just a trigonometric problem. And again, we'll hopefully have a chance to address that in the homework. So as the pendulum swings back and forth, there's this oscillatory behavior, and it's associated with converting the potential energy to kinetic energy, and then the kinetic energy back to potential energy, and so on. And if there's no friction, then this could continue indefinitely. And of course, for a reasonably sized mass and a reasonably low friction bearing on the swing arm, this can go on for some considerable amount of time. One thing that is useful to consider is there's something called the classical turning point, and that's the point where, according to regular mechanics, classical mechanics, that's the point where the system stops, where your potential energy is at a maximum and your kinetic energy is at a minimum. And that's where the system stops and sort of turns around. And so points sort of A and C on our little drawing here would correspond to the classical turning point. And that's a concept that we will return to in this course. Now let's also consider force and its relationship to potential energy. There's a lot of relationships, and they go a lot of different, there's this sort of complex web of interrelationships in really classical mechanics and quantum mechanics. And so we need to understand and be aware of all these relationships and be able to use them to solve problems. That's a lot of what this course will be about. So force is related to potential energy. The force along the x-axis is equal to minus the derivative of the potential energy along the x-axis, so dv dx. And of course, in 3D, it's going to be a vector quantity. So force would be a vector, and it would be minus dv dx. That's not supposed to be a 2. It's supposed to be a partial derivative symbol, dv dx times the unit vector I. minus dv dy, partial derivative of the potential energy with respect to y, times the j unit vector, minus dv dz, times the unit vector along the z-axis, k. So let's try to put this to work. Once we know the force, we can calculate the potential energy. And this will be something that we will have to occasionally do in the course of this semester. We'll be given some forces, and for various reasons, we might want to convert from force to potential energy. One of the real advantages of potential energy is that potential energy is a scalar. It has a single number at each point x, y, and z, whereas force is a vector that has x, y, and z components at each point in space. So it's more complicated to keep track of. So a lot of times we'll be wanting to switch from force to potential energy and back again, depending on the problem. And again, that gives us another route we can take when solving problems, another move we can make, so to speak. Okay, so let's look at an example of a situation where we know what the force is and we want to calculate the potential energy associated with that force. So let's look at a spring. Hooke's law. So we can imagine having a spring connected to some fixed point with a mass on the end of the spring. So we've got a mass. And at equilibrium, we have x equals 0. So we've set our coordinate system so that x is equal to 0 when the spring is at its equilibrium, and it can presumably be stretched or compressed from that point. So if we stretch the spring, then the force, again, given our definition of our coordinate system here, where x equals 0 is the equilibrium position where there's no force, then if we disturb the system, if we stretch the spring or compress the spring, there's going to be a return force, right? There's going to be a countervailing force that's going to pull the mass back towards the x equals 0 position. So if we extend our pull our mass to the right towards positive x, then there's going to be a force along the minus x direction, so it's going to have a minus sign. And Hooke's law states that the force is equal to minus some constant times the displacement from equilibrium. Again, we have to be very careful about how we define our axes, and that's why it's often good to have a diagram like this, where we can specify things like x equals 0 at f equals 0, or at equilibrium. So we can help make sure that things are not ambiguous, or that we don't make the mistake of starting with one set of coordinates, then switching to a different set of coordinates in a way that's going to give us the wrong answer in the middle of our work. Okay, so yeah, be careful about diagrams. That's why we have them. They can be helpful in keeping track of things. Anyway, so back to this. So we have a force is equal to minus some constant, which we'll call the spring constant, k. Now, k is going to show up a lot of places in this semester. In fact, you probably saw I sent out a sheet of a whole range of constants and the things that they can represent. They can represent multiple things. There just aren't enough letters in the alphabet. Anyway, so k here is a spring constant. We have to use context to keep track of that. There are other places where k is something called a wave vector, and then there are equations associated with wave vectors. Those don't apply in this case because this isn't a system that has wave vectors. This is a spring constant. anyway, so we have K is equal to this spring constant. And of course, you can tell that the units for spring constant would be newtons per meter, right? Because when we those would be the SI units for a spring constant, and that's something to keep in mind. And of course, you can go down to base SI units as well. And we can tell it's that because when we take our spring constant and multiply by displacement, which is going to be in something like meters, then we've got to get a force in newtons. So that tells us our spring constant has to be newtons per meter. It's good to keep track of units in these things. We can integrate to obtain an expression for the potential energy associated with a spring as a function of displacement, x. So since force is minus dv dx, and that's general for the 1D case, then plugging in our expression for force, we get minus kx is equal to minus dv dx. We can move the dx over to the right-hand side and integrate to get our potential, and we get potential is equal to the integral of kx dx, plus some sort of constant. And that gives us 1/2 kx squared plus some constant of integration. Now, when we do these kinds of integrations of potentials, we often will do it in such a way that any integration constant that we get is set to 0, and that's usually a convenient that's usually a convenient definition of sort of where the 0 is of our potential energy. And again, potential energy, of course, it's an energy. It's just a different kind of energy. So it has units. SI units are, say, joules, kilogram meters squared per second squared. Okay, and finally, I'd like to talk a little bit about, so that basically is a little bit of an introduction to classical mechanics. Some of these concepts we'll be using throughout the semester, particularly momentum, potential energy, and the relationship between potential energy and force. These will be things that we will return to. And of course, we'll often be using SI units or other units that are sort of historical, and but we'll need to know how those units relate to SI units. I'd like to close this part of a lecture by talking a little bit about Noether's theorem, or let's see the German pronunciation. I guess it's O with umlauts over it, so it's like Noether theorem. And her name is Emmy Noether. And this was a German mathematical physicist. Had to she was Jewish, had to escape from Germany to the U.S., where she was a professor at a university here. Anyway, so around the time, not too long after when Einstein had his famous year of 1905, the sort of year of physics. So a few years after that, she was in some discussions with Einstein, and she said she was working on trying to understand conservation of energy, and he strongly encouraged her to look into this, and agreed with her that there was something deep going on And so she was a well-trained mathematician. That said, there weren't really in Europe positions for women mathematicians at the time. She was kind of before her time, and but she nevertheless was working some with a well-known mathematician, David Hilbert, uh, who developed a number of concepts that are all over mathematics as well as physics, concepts such as Hilbert space. Anyway, so she was kind of Hilbert's star pupil slash coworker, and she developed this theorem that says for each continuous symmetry, there is a corresponding conservation law. And so there's a continuous symmetry of time in that if you take a system and then at all else being equal, you just sort of propagate the system forward in time and then look at its behavior, the outcome of any experiment that would be happening that you would form on that system is going to be independent of time. And so this, in other words, if you do something like, fire a cannonball, it doesn't matter when you fire it, the trajectory is going to be, the same, roughly speaking. So this symmetry of time, this continuous symmetry of time, because time can be varied by any amount, this, it turns out, she was able to show gives rise to conservation of energy. And the way that she shows this actually defines energy in an interesting way. It defines energy as this sort of mathematical transformation that you apply, or it's related to it's part of the mathematical transformation that you apply to a system to propagate it forward in time. Right? So energy is the sort of propagator, the infinitesimal propagator of time. So that gives us a more ultimate, although somewhat abstract, view of energy. So energy, sort of started off as a way to quantify the capabilities of steam engines, and was very much associated with work, like the work required to pump water out of a coal mine, that sort of thing. And but nevertheless, energy seems to be, and still you'll see in textbooks that energy is defined as, in say a Gen Chem book, it might be defined as energy is the capacity to perform useful work. However, that's kind of a circular definition because what's work, and sometimes work is given in terms of energy, and so that doesn't seem like a real sort of definitive answer for what is energy. But Noether's theorem does give us a better definition of energy and how it relates to space and time, and why is it conserved. And so she, in her proof, she defined energy as this thing that propagates the system forward in time, and showed that energy had to be conserved if time was continuous. Similarly, the continuous symmetry of translation, in other words, if you move your, say, your cannon around, it's not going to change how far the projectile can go with respect to the initial position of the cannon. And so that translational symmetry gives rise to conservation of momentum. Rotational symmetry gives rise to conservation of angular momentum. And as we may get to later in the course, we'll see that modern quantum mechanical definitions of energy are based on the sort of steps that Noether took in developing her theorem, improving her theorem. That we develop a time propagation operator that includes energy. And so this gives us a more definitive answer for, what is energy, and a few important facts. And one is energy is associated with time. The two are sort of completely intertwined. Sort of one doesn't really exist without the other. And we'll see that that also shows up in something called the Heisenberg uncertainty principle. And similarly, momentum is inextricably linked with position. The momentum is the propagator. It's the operator that propagates a system forward or backwards in space. And it is intimately linked with, momentum is intimately linked with position or translational symmetry of translation. And finally, we have an actual explanation for, even though the math is sort of beyond the scope of this course, but it turns out that conservation of energy isn't just something that was invented by Newton. By the way, Newton didn't invent the concept of energy. He got skirted somewhat close to it, but did not develop it. It sort of evolved slowly over the century or so after his Newton's Principia. But yeah, so conservation of energy, it turns out, is due to some fundamental properties of space-time. And so Einstein was a big fan of this work. That said, it kind of languished in obscurity and really hasn't been given the due respect, even though it was well respected in time. It sort of was sort of assumed, and proper credit, even though I learned these relationships about Noether's theorem when I was in grad school, they were not attributed to her, interestingly. Anyway, so that's the end of the first lecture. Next, we'll be talking about some observations that started to challenge this amazing edifice of physics that existed at the end of the 1800s, early 1900s, and that started to sort of put some cracks into the foundation, so to speak, of this amazing, amazingly successful set of theories, and ultimately upended all of physics, completely changed physics over the course of, and chemistry for that matter, over the course of 20 or 30 years. All right, so we'll talk about that next lecture, and that's the end of this lecture.